This video is going to be a review for statics on the reduction of a distributed load. A distributed load can be reduced down to a point load that acts at the centroid of the area of a distributed load. Technically, what we're going to be doing is effectively calculus, but we're going to do it without the integrals. Now, yes, if you know the equation of the line, you can always just take the integral to find the area under the curve. But we're going to try to do it without calculus because we don't really like calculus too much as engineers. So we have multiple different types of distributed loads. One of the most common ones, though, is called a uniformly distributed load because it is uniform in height. And we have a base width of x, and we have a height of our distributed load of w. So if we want to find the point load that this can be reduced down to, we simply have to find the area under the curve. So in this case, the curve is not really curvy, it's very flat, right? This is technically, if we wrote the equation of the line, this would be y is equal to just some random number. So we like to call this a 0-degree slope because it has x over here to the 0th power. So it is a 0-degree slope, so it is just absolutely flat. And in this case, we know that our area for a rectangle is just base times height. So we have the base as x and the height as w, and that is literally just our area. So that's going to give us a force resultant. We'll call that Fr. And that is going to act at the centroid of the area of the shape. And you should know by now that the center of a rectangle is right here at the dead center. So we're going to have this force resultant acting right there at the dead center. So again, C is at 1/2 of the base, which for us, that's 1/2 of x. It's that simple, right? That's all there really is to it. But it gets more fun when you have more fun shapes. So another more fun shape that you'll see all the time is what we like to call linearly distributed, because it is a linear slope, so it is linearly distributed. And again, all this actually means is that this is now a first degree sloped line. So again, that means that our equation for the line is y is equal to some number times x, and it also could have plus some number as a constant. But this is x to the first power, so this is a first degree slope. What does that do for us? Well, it doesn't actually change much. We do, though, have two different points that we have to consider. We have the smaller side and the bigger side. I'm just going to call them O and P. Just for the sake of keeping up with where we're going. And O is at the smaller size of the triangle, and P is at the bigger side of the triangle. But long story short, still, we just need to find the area under the curve. Now, I'm pretty sure everybody is aware that the area of a triangle is 1/2 base times height. Again, our base is still x, and our height is still w. So our area equation is simply 1/2 x times w. Yes, and that is, again, our force resultant, and that force resultant acts not at the center. Yes, the area of a triangle is not distributed very evenly. Instead, it's actually over here somewhere. So we actually do have a force not centered. Yes, so that resultant force would be somewhere over there. So now the question becomes, what's the distance to C? Well, C kind of depends on which side you're coming from. Are you coming from the distance of O to C? Or are you going from P? Which one do you want? Of course, that just depends on the problem, right? Do you want the distance to O, or do you want the distance to P? And the distance to O is the bigger side, and that distance is going to be 2/3 of the base, and the base is x. The distance to P is simply 1/3 of the base, and again, the base is x. If you add the distances to O and P together, you are going to get the full length which should obviously make sense why, because it's, of course, at one particular spot, not moving. So there you go. So those are the things. Now, technically, there's a trend here that you may or may not be noticing that's going on. You'll notice two things here with our trend. Our area for 0 degree is simply base times height, right? I guess up here, base times height. Whereas our 1st degree is 1/2 base times height. What's really going on is you can just imagine that there's like a 1/1 here in the front of our rectangular equation. And you'll notice that this bottom denominator went up by 1. So yes, in fact, we could actually do the same thing for a quadratic. Yes. This is assuming it's a very basic shaped quadratic, but this would be a quadratic in shape. So again, quadratic would have a total W up there, starting from 0, total distance of x. Still going to call O the one on the left, still going to call P the one on the right, the bigger side. And again, this is a 2 degree slope. And the 2 degree does mean that our equation is y is equal to some number x squared plus some number x plus some number. So again, the 2 degree comes from that squared term. So you're thinking, ooh, okay, so if this one's a 2, then the area should be 1/3 the base times the height, and you'd be correct. In a way, actually, it's kind of funny at this point, it kind of changes. The area of 1/3 base times height is not the area that you think it is. It's actually this part here. Yes, it's actually this glorious shape on the outside, this smaller half, if you will. So that is actually not what you're wanting. No, not at all. And in fact, if you want the actual area that we're trying to solve for, so it's not that one, it's actually going to be the opposite of that. So if it's 1/3 the base times the height out there, then what we're looking for is actually the 2/3 option of base times height. So again, that's going to be 2/3 the base of x, the height of w. And that's for a very generic x squared shape. So a very generic quadratic shape, and you get 2/3 the base times the height. And that's all cool and all. So where is the mystical, magical centroid? Well, yep, as you guessed it, it's definitely closer to the larger half. That's where our resultant force is going to be acting. So our resultant acts way over here at C. Where is C? Again, the distance to C from O or P obviously does matter which one you're talking about. So let's do distance to O. It is the bigger one compared to the distance of P, as you can tell. Is there a trend that we can catch on to from before? Well, let's go look. If we had, for our rectangle, our 0 degree, 1/2 of x, and then again you just call O, still there, P over here. It doesn't actually matter, right, because it's equal, but whatever. Still, the distance to O is still 1/2 x, and if you go to the 1st degree, you realize that the distance to O is 2/3 x. Now maybe that one's not very clear, so let's go look at it in terms of going to P. So what do we have for P? Again, for the rectangle, it's still 1/2 x. When you go to the triangle, you get 1/3. Okay, so what happened? Well, we started with 1/2. We added an additional 1 to the denominator. So yep, if we're going to go to P over here, you can guess it. P is going to be 1/4 of x. Yes, we're just literally adding 1 more. Crazy. And then obviously the distance to O has to be whatever 1 minus that is. So that's 3/4 of x. And you can continue to do this for any shape. So like when you get later on, if you want to find for 3rd degree, they look pretty much similarly to quadratics. But again, you just have to pay attention to the fact that your area is just going to go up 1 more, and so is your distance. That's literally all there is to it for that one. But we can have even more fun shapes than that. Yes, it doesn't just have to be increasing in powers. We can have some fun ones. And by fun ones, I mean we can have Things like trapezoids. Yes, those ones are not exactly any particular degree, right? I mean, they are technically still a 1 degree, but it's a trapezoid, so that's kind of awkward. So instead of just having one W, we have a W1, and we also have a W2. Still have X. We still have O on the smaller side, P on the bigger side. And you're thinking, oh, there's going to be a magical equation. I know the area of a trapezoid. This will be a joke. To be honest with you, I don't remember the area of a trapezoid because it's really irrelevant. You see, as you get later on, you're going to realize that all of these complex shapes pretty much boil down to the basics. And what are the basics? They're right here. Mainly, it's a uniformly and linearly distributed load. You can do so much fun stuff with these two shapes. And we like to do what's called superposition. And how this principle works is you take a hard problem, namely this trapezoid shape, and you break it down into 2 or 3 or maybe 4, it doesn't really matter how many, but you break it down into multiple smaller problems that are simple. So for instance, I can just draw a line right here, and I can break that up into a uniformly distributed load and a linearly distributed load. And they're just acting right on top of each other. Yep, that's it. They both go over the distance of x. The uniformly distributed one has a height of W1, as you can clearly see, and the triangle, we're only looking for this height right here. So that's going to actually be W2 minus W1. That's the total height of the triangle. Yes, all you have to do is actually add them together. So if you were to find the two forces for the resultant, they don't add together. They don't add together because they're not acting at the same spot, right? The centroid of the uniformly one is at the dead center, whereas the centroid for the linearly distributed one is kind of off center. So we're going to have two separate forces. We'll call this force resultant 1, and we'll call this one force resultant 2. And they don't themselves add together specifically, but they will both act on the same line. So what we're going to have is we're going to have force resultant 1 be right in the center, and then we'll have force resultant 2 be off center, where he's a distance of 1/3 of x over here, and this guy is 1/2 of x. So again, if you're just going to sum some forces in the y direction or do whatever else you're going to do with it, all you have to know is that those two forces are existing now instead of just one. That's it. You could technically sum them both all into a corner because it really doesn't matter. It's just some equilibrium equations. But effectively, to solve any problem, you just need to break it down into some itty-bitty pieces and compile them all together. And that is how you reduce a distributed load.